The gravity of the time is such that every new avenue of peace, no matter how dimly discernible, should be explored. Never before in history has so much hope for so many people been gathered together in a single organization. You will provide a great share of the wisdom, of the courage, and the faith which can bring to this world lasting peace for all nations and happiness and well-being for all men.
So we are here today with Dan Stout, the Director of Nuclear Technology Innovation at TVA. Dan, welcome to Titans of Nuclear.
Well, thank you. Thank you, Brett. Appreciate it.
No, it's great to have you on the show. I, of course, have been reading about all the great work that you've been doing. But before we get into that and your current work and understanding SMRs, maybe we could just talk about you and how you got into this space. You grew up through the Navy program, right?
I did. I went to the Naval Academy and then served in the submarine force about 6 years. Qualified on 3 different reactor designs while in the Navy, and so that got my start. And then I stayed nuclear. I worked in the uranium enrichment business for about 15 years, and again in a technology innovation kind of area. I worked on 4 different uranium enrichment technologies.
Wow. What are the different uranium enrichment technologies?
Gaseous diffusion is the old one that was the backbone in the United States, but then shut down. I worked on AVLIS, which is an atomic laser process, Silex, which is a molecular laser process, and then gas centrifuges.
And gas centrifuges, that's got to be the one that's used most commonly now, right?
Correct.
And the main advantages between gas centrifuges and gaseous diffusion, the old technology, is it just energy input? What are the big differences?
Yeah, gaseous diffusion was capital intensive and energy intensive. So I had high capital and high operating cost. Centrifuges have high capital costs, but lower operating cost.
Got it. And the centrifuge technology, I mean, it's, we hear about it sometimes in the news. I guess, something's spinning. You see these, person-sized canisters lined up across a football field's worth of area. Am I thinking about the right stuff here?
You are, and they come in different sizes. Russia basically had a smaller design, and the United States evolved to a very large design, but they all work on the same principles.
And who manages that? Is there like one place in the world where it's mostly done, or does each country have their own set of centrifuges?
It's very sensitive technology, so there's generally tight controls over it. So that Russia, China now have their own developed technologies. Commercially, Urenco is the leader, the European base, but they also have a facility in the U.S. And then residual from USEC, now Centrus, they have a technology that's based upon DOE's design, and they're working on demonstrating that.
And as I understand it, the nuclear fuel is kind of like a commodity market where, each stage of it, from the mining to the enrichment, can kind of just be, purchased like a commodity. And, these things, I guess, they know how to move around from factory to factory, but the person who wants to acquire the enriched uranium at the end of the day, they can essentially, put in an order and the things all happen. Is that an accurate description?
Yeah, I pretty much, the mining, the enrichment, the conversion, they pretty much are commodities, fungible commodities. Some of the suppliers like to view their value add as a product, and so how things are packaged and bundled is slightly different, but the material itself, it's a commodity.
And one thing I've been dying to ask an expert in the space, so this is a perfect time. The current cap on enrichment, this 4.95%. Where did they come up with that number? Why is that what's okay, and 6% is not quite okay? What's going on there?
Well, we could spend a whole hour on that. But it kind of evolved, and there's a lot of institutional barriers, whether it's transportation package limitations, or lots of NRC licensing codes for criticality safety, or lots of reasons that and so after many years of it being the limit, it became the limit.
Yeah. Just not because there's any fundamental reason that 6% is bad. It's just the whole supply chain and best practices are built out for the equipment configured to go up to 5%. So the investment hurdle to get 6% might be pretty significant.
Exactly. I mean, that barrier will be broken at some point.
Yeah.
But it's a matter of these institutional things being broken down bit by bit, or some entity, making an order for large quantity, and then all the commercial solutions will prevail.
But, like a market-driven.
Pieces and parts are being addressed. I know enrichers have gone above 5. I know fabricators have gone above 5 in their licensing and so forth. So it's happening.
And at the end of the day, because I know a lot of the startups out there want to use, let's say, up to 20%, which I still think is classified as low enrichment.
But it's called high assay, low enriched uranium. So 5 to 20, yeah.
And the advantages that they see in that are just better characteristics for the geometry and material selection in their core. Are we able to use those same centrifuges in order to get that high, or do we need to switch to like a laser-based system?
The same centrifuges can be used. It's how you configure them and plumb the gas. You need to stage them vertically and feed in a higher enrichment level to take it to the next step. So, centrifuges and gas diffusion, I mean, it's all about staging to continue to step up the enrichment levels.
I see. And that's because at the end of the day, you're separating out the U-235 from the U-238. And you do just this in a piecewise fashion, since they're chemically identical, and they're so similar in every respect other than that little bit of weight. That's what we're taking advantage of essentially in this centrifugal process. And that's just a little bit by bit to eke out that extra level of separation. Is that accurate?
Yeah. And one of the, in theory, on the laser processes, you might be able to have the energy or the laser being absorbed only by one of the isotopes. But you might be able to be a little more efficient from that alone, relative to the gaseous diffusion and gas centrifuge, where you're physically handling all of the material, all of the mass, and so there's things like that are important to the developers in enrichment.
Cool. And then whatever happened to the laser stuff?
Atlas was shut down, and it was really hard. It's dealing with molten uranium, highly corrosive, very high temperatures. So it's hard to come up with a system that could have high reliability long term. Silex, which is now Global Laser Enrichment, it's still in development. So I don't know the details.
And so you spent a large part of your career in this enrichment process. What came next for you?
Department of Energy. I got recruited to go there and serve and so it was an opportunity to serve the country. I was responsible for the back end of the fuel cycle, reprocessing, recycling the used fuel. It was a kind of a startup program. My role was more involved with interfacing with the industry on different designs and capabilities to, should the country make it a policy priority to get back into the recycling business, what that would look like.
And what are the pros and cons of recycling?
Well, one of the pros is you can get to reuse a lot of that energy that's still in the used fuel. The biggest con is it's pretty expensive. You're handling materials that are highly radioactive, and after it's fissioned, you got a lot of different elements, and how to separate out the ones that you want to remove and retain the ones that are valuable for generating energy again, and dealing with all those waste streams that come out of a process that does that. It's hard to do. There's also the ability to misuse such a process. You could, it could be misused for proliferation, nuclear weapons, that kind of thing. And so there's pretty stringent controls needed for safeguards and security. So those are the big cons. On the other thing, on just the pure economics, uranium is pretty abundant.
Yeah,
and
as abundant as tin.
Well, it's abundant. It's in seawater. You could mine it out of seawater, and you kind of know what the cost of that is.
Yep.
And reprocessing and recycling the used fuel, getting value out of the recovered material, it has to be better than mining it out of seawater for it to make economic sense.
Right.
And it's not, who knows?
Yeah, I think a lot of this, what this always comes down to, are the economics at the end of the day.
Yep.
With the recycling, one thing that I've never understood, and maybe you can tell me, because I'm still always hunting around for answers when I've got kind of an idea about something, I want to see if people have thought about it before. And I never understood, why don't they just take the spent fuel and just like throw it in a crucible of some sort, and it heats itself up? Like, why wouldn't everything just kind of like separate out over time in like nice, neat layers, and then you just kind of, vent out the radioactive gases into a nice, little canister? You can scrape off, or wash off the liquids, scrape off one solid layer after another, and then you're just left with whichever layer you want. Is that something that's ever discussed?
Yeah, I don't know when this was, probably in the 90s, but there was a company called Molten Metal Technology, and that was their concept.
Okay.
And I think they went bankrupt. I don't know. So it's definitely been thought about, and there is some technical merit to that concept, right? But the devil's in the detail. What kind of bad reactions could take place? What kind of crucible can contain the temperatures, and what kind of gases are coming off? What kind of process and system do I need to wrap around such a process? So I don't, good question. I don't know the answer, but there was work done in that space.
Well, you're the first person to point me to it, so I'll definitely have to track someone down from that organization to get a whole interview with them.
Sounds good.
That's great. Yeah. So what led you to your work at TVA?
So while I was at the Department of Energy, TVA had some interest in what the department was doing on recycling used fuel, and so I made some contacts. They recruited me to join the TVA team, and I think it was 2009. So I've been with TVA now a little over 12 years. It wasn't long after I got here, the opportunity to work in new nuclear came about, and so 2012 on, I've been responsible for our new nuclear activities.
Cool. Okay. Well, I really want to dig into that. But before we do, can you just tell me a little bit about the history of TVA? What is TVA?
It's created in 1933, part of the the New Deal. It was a public power model with the focus on helping to bring electricity to impoverished area of the Tennessee Valley, and to provide not only electricity but also protect the environment and provide for economic development. And protecting the environment included things like controlling the Tennessee River, which had lots of floods, and so we put in place a series of dams and provide flood control, and we do that today. In fact, last year we estimated we avoided over $1 billion of flood damage, and so we continue to win industry awards for economic development activities that we do in collaboration with our local power companies who are our partners in providing the electricity to the companies and the citizens of the Tennessee Valley.
And is it's pseudo government owned, or what's the relationship with the federal government?
Yeah, we're 100% U.S. government, but we get our money, our revenues from electric bills. It's almost in its entirety. It's the electric bills that provide for all of our costs, and we operate as a nonprofit. So we do provide these additional services that are a little above and beyond what other utilities do in terms of flood control and environmental protection, and we support recreation in the Tennessee Valley, access to the river system and things like that, that all part of this economic development, environmental stewardship, and low cost, reliable, and affordable electricity.
I mean, I love that all those things are paired together, because so often energy has some relationship with the natural environment. And you don't listen, I'm all for, free markets and capitalism, but sometimes you do want the government to protect certain things, like things that are good for the common good, and the environment is one of those things. And so it seems actually a natural pairing to have this specific relationship. Has the TVA model been replicated elsewhere throughout the country? I can't imagine the Tennessee Valley is the only area where power and the environment come into potential partnership and conflict with each other.
Well, there is no other model quite like ours. There are a couple similar. You have the Bonneville Power Administration out west, which is an arm of the Department of Energy, and some others that I'm not an expert on what the differences are, but there's the Western Area Power Authority. So there's some other authorities that are somewhat similar, but TVA is unique.
And because it's closely tied to the federal government, does that mean it can be a sandbox or a testing ground for other government energy related activities? Like if the DOE wanted to, pilot something, whether it's nuclear or whether it's anything, carbon capture or, some sort of, high voltage, renewable power line or something, is that type of relationship in place where it's like, okay, we're going to TVA and we're just going to do it there?
The opportunity is there. I mean, TVA is an independent agency. We do have a presidentially appointed, Senate confirmed board of directors, and then a full-time chief executive officer that makes the day-to-day decisions of how TVA works. And there is opportunity for us to work in collaboration with other government agencies, and we do that. We have been supporting national defense in a number of areas. And, one example is tritium production that's used to support the Department of Defense, where we use our nuclear reactors to help in the generation of tritium and support that kind of activity.
Cool. Okay, so there's precedent. I mean, that's a great start. So, all right, now let's get to the meat that everyone wants to hear about: SMRs, what you've been doing with SMRs, and maybe, I think as we were alluding to, is it possible that, I know like it is in the best interest of the government to promote the development of SMRs. I mean, is there conversation about using TVA as a testing ground for this?
Well, absolutely. TVA has been making progress on activities in that space. We did prepare an application to the Nuclear Regulatory Commission on a site, Clinch River site in Oak Ridge, Tennessee, and the approach we took is plant parameter envelope. So it's a flexible approach that can accommodate more than one reactor, more than one design, and the NRC issued that permit in December 2019. It had a couple of unique elements within it. That one of them is our unique approach to emergency planning.
Tell me about it.
We thought it was important to challenge the regulator with how the significant improvements in safety that how that could be realized, in a manner that continues to protect public health and safety as the highest priority, but recognizes that that can be done without larger emergency planning zones. And so, we thought that it should be a function of the dose to the public, as was the basis for large emergency planning zones. And, if we could do the calculation and show that the dose was, of meeting the regulation or better, at a location closer into the site, that ought to be the basis. And so we put that forward in our application. And when we were doing the preparation, we learned that, there's a break point on if you can get to the site boundary, then the programs that are needed for offsite activities, they can go away.
When you say get to the site boundary, you mean if you can keep the maximum anticipated dose under a certain threshold at the site boundary? Is that what you're talking about?
Yeah. So you basically,
what is that dose, like 25 rem or something, or what's the?
Well, it's complicated, but a lot of it comes down to 1 rem.
Okay.
But there's other criteria, 25 and so forth. The same bases that are used for protecting the public beyond 10 miles from a large nuclear plant, you can use that same basis at the site boundary. If you can demonstrate to the regulator that the safety to the public beyond the site boundary, it's similar to what you have beyond 10 miles from a large plant, then there's no need for, we do all kinds of activities to protect the public within 10 miles of our large plants. But beyond 10 miles, there's still things that are done and part of our plans, but it's a lot less. So what we learned is that you're actually protecting the public better. Let me talk about Fukushima briefly. I mean, there are some international studies that have shown that the impacts to the public from the evacuation, a lot of that was due to the evacuation itself. If you compared that to what kind of exposures and health impacts would have occurred if the people had not evacuated, there are impacts, and it's possible that there were unnecessary evacuations that led to more adverse health impacts. So, it's an evacuation's a big deal from a public health and safety perspective, and avoiding unnecessary evacuations is actually an improvement in protecting your public.
Yep.
So those are hard conversations to have. We worked really hard with the state, with the locals. There were meetings with the federal agencies involved in emergency planning, and it's a hard conversation to have. But we had those. We had the residents around the plant. One of the things we did, we had a barbecue, hamburgers and hot dogs. Me and my team were out there meeting with the locals, and we sent a letter to everybody that lived within a mile and a half of the plant, and had all kinds of conversations with the locals. Learned a lot of things.
And this is which plant is this? This
Clinch River site.
So there's a plant already on Clinch River.
No, this was our part of our planning for the early site permit at Clinch River.
Got it. And so how is Clinch River chosen out of all the area that TVA manages?
So there's a very detailed site selection report in our application, but it's a good location in terms of it has access to water. It's in a community with strong public support. There's good access to transmission. It's right beside the Department of Energy's facility that uses about 100 megawatts of electricity. So, it was a good location.
That's awesome. Okay, so you picked that location, you had your barbecues, you got public buy-in, and then put together a whole package, submitted to the NRC, and then they give you the approval?
Yes.
That's amazing.
Just like that.
I mean, I'm sure it's a lot harder and a lot more expensive, but an amazing success story, because in our country, we don't get to hear too many great success stories around nuclear making progress. I mean, nuclear is a success story every single day that it operates because of its low environmental impact, its low carbon footprint, clean, steady power, baseload generation. I mean, the list can, energy security, the list can just go on and on and on and on. So there's always a success story, but you don't hear about the steady state success stories. And we don't get too many something new happen success stories. So this is probably the most exciting thing that's happened in U.S. nuclear in the last decade, maybe.
Well, I appreciate that. And we're happy with that, but we got a long way to go before we have electrons on the grid.
Okay, so tell me. Okay, what are the next steps? Because I want to see this happen. I want to see some SMRs built. What do you got to do?
Well, the next step would be getting, we kind of view the the early site permits kind of like a zoning permit, and then you got to get the construction permit. And so that's next. I mean, you have two options there. You can get a combined operating license, COLA, or you can get a construction permit. The construction permit requires a little less detail on the design and enables moving forward a little earlier. The combined license, that requires more detail, especially about the operating license and the programs that you need for that. Either of those would work and can use the early site permit information within them. So that's the next step. And then if we went with the construction permit approach, there would be a subsequent operating license. But the construction permit, that's about a 2-year task for us with an existing early site permit. And then, the NRC review and approval of that, probably another 2 years. And so construction, that's still at least 4 years away. And in the meantime, go ahead.
And why should it take so long? Is it just because a vendor doesn't have a design quite ready yet? I mean, if a vendor had a design ready to go, what would it take to get that permit in place?
It's a good question. I mean, does it really need to take that long versus what has it historically taken? Right. And so the dates that I just threw out there, 2 years, that's pushing the NRC to be more nimble than and more aggressive than they have traditionally been. And frankly, the NRC has been doing a great job of improving on their schedules and their schedule discipline, but it's still long. Does it need to be that long? Who knows?
Yeah, because one of the things that I love about the SMR story, I mean, I actually like the big reactors too. I mean, they produce a lot of power for not that much, not that much material consumption or footprint. But one of the ideas that I love about SMRs is that they could perhaps qualify for a reduced risk envelope. There's not as much heat, you don't need as much coolant. Like there's just a lot, you don't need as big a containment. Like there's just a lot of stuff that I feel like could be used to present to the NRC to say, can we treat this differently than the big reactors? Because can we just all acknowledge up front that the reason that we go through all of this intense scrutiny of a big reactor is because of perceived big consequences. I could argue with that too, but let's just give them perceived big consequences. But with the SMRs, you could argue that we're in a totally different consequence envelope. Like what really, because I know you've put so much thought into this, what really needs to be demonstrated to demonstrate the safety of an SMR? If we're talking, and I'm saying really small, I'm not talking like SMR, like 300 megawatt SMR. I'm talking like 10 megawatt, you can maybe call them micro reactors. There are a lot of companies out there that want to do this. What do we really need to show to prove the safety of a 10 megawatt SMR?
I mean, it's really about providing benefit to society and protecting society from the hazard in balance. And that's the tricky part. So I don't envy the NRC their challenge of making sure that they're protecting public health and safety, but resisting the temptation to ask for and demand the detail and the testing that large plants warrant that small plants don't. That are, when I say small plants, safer designs, and that level of detail is the key to the time and the cost associated with licensing.
Like, would you guys offer to, given you guys have gone through you have NRC experience, you got the early site permit, you have operating experience, you have several reactors operating. Is TVA looking to help some of the new vendors get through the NRC program? Are they offering financial support, intellectual support? What's TVA's level of participation in this?
That's it's tough for utilities to bear significant risk. There are utilities in public power markets where the competition is stiff. The markets don't allow for long-term thinking, and so they don't have big R&D budgets to go help. In the regulated markets, the public utility commissions often don't allow the utility to get any kind of return on R&D kind of activities. I mean, so we've evolved in the United States to this structure where utilities aren't afforded the opportunity to do pure R&D or take high risks. TVA, with its public power model, can be a little more forward-leaning in that space, but not a lot. And so, as we look at new technologies and we assess the economics and the risks, and that's of the product itself, but also the team and the risk associated with the successful execution. And so, we've been continuously evaluating the different options over the prior 4 years. And we concluded that the light water SMRs have reached the point where they're ready to move on to that next stage of demonstration. The reactors that use other coolants, we still have some concern over the risks. The risks, particularly on fuel.
And when you say risk, you mean like economic risk. You don't mean like safety risks, right?
Correct. I mean, economic risk. I mean, uncertainty associated with the schedule and the cost.
Right.
And so, if you look at the fuel component itself, I mean, enrichment levels, shipping containers, the manufacturing predictability and supply chain. And speaking of supply chain, I mean, a lot of the new designs don't have supply chains. The whole establishment of a supply chain is a big undertaking.
Yeah.
And then the licensing pathway and the confidence and the predictability of that. And so we see a clear distinction between the light water SMRs and the non-lights. And, so, that's where we're at today.
Yep.
And that becomes important from a business perspective as well, because there's increasing urgency to reduce carbon emissions. And as the urgency to reduce carbon emissions increases, that leads you to make your decision sooner rather than later on which technology type, and that you assess the risks today. Now, we like some of the new technology designs a lot. They have potential to have better economics. If you think about the major drivers on economics, they have to do with the pressure of the system, the temperature of the system, the power density. And, if you can come up with a design that is low pressure, high temperature, high power density, you have much greater likelihood that you're going to have less concrete and steel and, something more economical.
Yep. No, I love the first principles thinking. I mean, my team went through a similar exercise. I mean, of course, we got to benefit from you and people like you and reading all of your reports. But we've come to similar conclusions. From a first principles analysis, you can see what will drive cost in the system, even if you haven't necessarily built the whole thing out. And we've narrowed it all down to simplicity and supply chain constructability. The boring things, not reactor design, which everyone seems to want to do, but doesn't seem to be the most influential factor in the overall cost of your system.
Right. That's right. And then, there's the size, right? And there's lots of things to consider in the best size. When you get really, really big, mega project risk becomes a real thing. And the ability to manage that many moving parts, or the risk, the consequence of messing up in one area. And, so mega project risk is something to avoid. Now you get too small, then you have part count. You got too many parts and components for each individual unit. And, the sweet spot's probably in the 200 to 400 megawatt range, where you can get your balance of plant essentially off the shelf. Yeah. And you take advantage of that economy of scale on the balance of plant, which is a huge chunk of the cost.
Yep. It's so funny to hear you say that. We came to literally the exact same conclusion in terms of size as well. One of the things that I want to hear your opinion on, because one of the things that we figured is that while the sweet spot is probably that 200 to 400, in terms of just getting a project off the ground, going smaller might be easier. You're not going to be as cost effective. Your LCOE is going to go up. But you know what? Like, nuclear is so, like, the fuel is cheap, compared to other thermal power sources. So, like, you've got a little bit of extra room to play with anyway. So why not, let some of you, why not produce a suboptimal system, but that's just a little smaller, a little simpler, a little easier to get the pipes in, the parts in, load the steam generator into a normal sized building. Have you guys considered that as well? Saying, actually, we'd almost prefer something that's sub 100 megawatts, even though we know the ideal is 200 to 400.
Yes and no. I mean, from utility perspective or a TVA perspective, we have to operate within our governance parameters, right? We do least cost planning, we do an integrated resource plan, and we look at our alternatives. And so, if you're too suboptimum, how or why can we invest in it, right? And so, if it's the least cost option and good enough because it's low risk, it's a simplified, robust design that you have high confidence with low risk. That's cool, but is it still low cost? In other words, can we go invest in that? So, one of the things with new nuclear, it gets back to your earlier question that I didn't answer right. That, I think there should be public-private partnership in first of a kind in nuclear. And so if the federal government taxpayer were to bear the lion's share of the first of a kind risk, TVA, if we can protect our rates, our electric bills that pay for our operation, that balance can be achieved, then TVA has a role to play in first of a kind demonstration.
Yeah. It seems to me like a good justification could be made that, investing in one of these small systems, even if the project doesn't work out altogether, won't lead to any increase really in what the ratepayer pays, just because it's a small project relative to the overall expenses. But if it does work out, the reward is so great, because then you've got a model that you can replicate throughout your network in order to significantly reduce costs moving forward. So it seems like a low risk, a high reward payoff, which seems to me like that checks the box for a great investment.
I agree. I mean, you got to have confidence that the nth of a kind is going to be economical.
And so if a vendor wants to come to you and make a pitch, how would they do it?
Got my email. My phone number.
Yeah.
So, we actually are embarking on a TVA environmental review process. And so we went through a public scoping, and March 1st, we had a public meeting, and now we're in the process of developing a draft environmental impact statement. And it's for a nuclear technology park at the Clinch River site. And
awesome.
Within our 800 megawatts of our early site permit, we see the opportunity to demonstrate more than one reactor, more than one design, but it has to be packaged, ready, design mature, reasonable risk, and we got to have the contractual approach that's going to protect the ratepayer of the Tennessee Valley. And if we can, within those guidelines, if a project can be bundled, makes good sense to get the demonstration done, that's what we hope to use our site for.
Amazing. And what is so that's TVA and your site. Actually, one more question is on the physical characteristics of the site itself. So you're permitted for up to 800 megawatts, chopped up into different SMRs. What is what's the land area that this park encompasses? How many acres do you guys have?
It's about 935 acres of area where we can do things. And we've kind of broken it into two distinct areas within that 935 acres, where you have the better topography and characterization, and so that's what we're looking at, is how to use area one, how to use area two. Do we want to do both? And then there's some other elements that before we get into decision making, which is in the future. Do you really want to be managing two or three at the exact same time? And so it's important for TVA. We view it as very important that you have successful project execution, that delivering on cost and schedule to establish confidence in subsequent projects and from the investment community. We've got to make improvements in that area. And so TVA is spending a lot of time and a lot of analysis and a lot of planning to make sure that when we pull the trigger on execution, that we can do it in a manner that achieves those results and helps the industry gain credibility and confidence from the investment community and for subsequent projects.
And what about grid integration? Oftentimes it's left up to, like, if there's an independent power producer that, tries to connect to the grid, they've got to pay all these fees to literally connect the wires to the local substation. Would TVA handle that for a new nuclear vendor?
Yes, that is our business. And, the Clinch River site's at a good location for connecting. We have 500 kV transmission and 161 kV transmission that are on site. So, the substation and the connection to those is something we're prepared to do.
And as far as various licensing paths go, I mean, my team has been trying to understand for these SMRs and for the first of a kind deployment, what the various options are. If it's possible, instead of going through the traditional commercial NRC framework, if it makes sense to apply as almost like a research reactor, given the innovative nature of a first of a kind SMR. Perhaps the research reactor methodology is a little bit more lightweight. Is there the potential of, because DOE has their own licensing infrastructure, such as that they'd use for the versatile test reactor, is it possible that DOE could lease part of your land to make it technically DOE land, so it can still be in part of your technology park, but they've got the authority to be the licensor of record? Is that any of that possible?
I suppose it's possible. It probably would go the other way better. I mean, one of the risks that everybody ultimately needs to address is NRC licensing. And so if you get a DOE license, you still have that risk remaining on NRC license. And with our early site permit on our land, we do have a pathway that's probably actually more streamlined than if DOE were to start from scratch on different land.
Got it.
But at the end of the day, I could envision that we could give the land to DOE and the D&D liability of that test reactor.
Yeah. And you say
maybe there's some opportunity there where that could continue to service DOE into the future.
Got it. And when you said D&D, is that decommissioning and okay. Got it.
Yeah, that's one of the things that a utility needs to think about on one of these smaller test reactors that really doesn't make much revenue. And the D&D cost alone might be as much as all the revenue that you get from something really small.
I see, because the D&D revenue is not proportionate to power output. It's just a fixed rate or something. Is that the idea?
Well, you don't know. I mean, there's some uncertainty on what you're going to have to pay in advance for your decontamination, decommissioning, and then what's the ultimate cost of the waste associated with an advanced reactor. So fuel forms are different. So there's, again, we have a good handle on light water fuel.
Yep.
We know fewer unknowns on light water. With advanced reactors and different fuels, there's more unknowns.
Yep.
Especially on the disposal side.
And underground. Talk to me about underground. I saw on your website, because I've scoured your website and all your documentation, I noticed that you mentioned one of the advantages of SMRs is underground. Can you maybe talk to me about that and help me understand? Because digging underground can be expensive. Also, can you help me balance the cost and the benefit of siting something underground?
Yeah, I think it definitely helps with safeguard security, aircraft impact, those kinds of things, and your analyses to dose for emergency planning zone, things like that. There's some benefits, but in terms of cost, great point. So we are very interested in advanced construction methods, participating in a project that isn't yet underway, but to do vertical shaft boring. Some of the technologies and techniques that are used in the non-nuclear area, see that as a great opportunity to expedite construction and reduce cost. And if you can do a vertical shaft boring and avoid the need for a bathtub type excavation, the amount of dirt handling and engineered backfill and stuff is significant.
Yeah.
And those types of technologies are used, and you make a tunnel underneath the English Channel, or subway system, you name it. So are they safe? Well, you have people in cars under tunnels, and So, we got work to do to enable the NRC inspections where the building wall meets the basement and all that. So I am hopeful that there will be a demonstration and work done with the regulator and to reduce the risks on that kind of advanced construction method, which is one of the keys to keeping the cost down for solving this whole thing.
Yep, absolutely. And then what else excites you about, some of the technology and innovation coming down the pike?
Yeah, advanced manufacturing, it's wonderful. I can see all kinds of opportunities on how that might improve on cost and schedule. At TVA, we did work with Oak Ridge National Lab and Framatome, and we did use 3D printing, make a channel fastener, put it in Browns Ferry. We're right now actively looking for our next part and our next challenge, trying to ratchet up and get something more significant to safety, and challenge the regulator to get comfortable with moving along in additive manufacturing and its application in nuclear. I think artificial intelligence and machine learning is going to revolutionize a lot of things in the economy. But in nuclear, the ability to move from how we do preventative maintenance today and to capture the data and to be able to analyze the data and use a digital twin, and that excites me. I think that there's a lot of opportunity to actually achieve the efficient operations and maintenance cost using these techniques and putting the right processes and systems in place up front. If you look today at the U.S. nuclear fleet, how many warehouses are there and supply chains, and how many parts are there that if you were able to truly standardize your plant design, if you're able to put in place an Amazon Prime for maintaining, we can get so much more efficient than what we are today. And so those things excite me. And I think the intersection of the artificial intelligence, machine learning, and a commitment of like-minded owners to that vision is going to lead to the efficient O&M in the long run.
Awesome. And as we wrap up here today, Dan, can you just tell us, in your words, why is nuclear important?
Well, it's one of those technologies that has tremendous power generation capability. We have been using it for a long time. When you make your electricity in a manner that's clean and reliable, the world prospers. You're able to make a significant difference in carbon reduction. If that's important to you, well, that's the way to do it. And if you look at carbon emissions, about 70% is transportation and heat. And, nuclear is a way to enable the electricity sector to be electrified, be 100% carbon free, or get towards 100% carbon free while keeping costs reasonable, which enables you to electrify the transportation sector and the heating sector and truly make meaningful change long term. So it's a great technology. I hope to see it deployed broadly and help the United States and the world prosper.
Dan Stout, thank you so much.
Thank you.
And initiate at least a new approach to the many difficult problems that must be solved in both private and public conversation if the world is to shake off the inertia imposed by fear and is to make positive progress toward peace.